Can you introduce the speaker?
Sure. Good evening, everyone. So it's our pleasure to introduce the speaker in this special functions and number theory seminar today. It's Sonika Dhillon from ISI, and she'll be talking on linear independence of numbers. Over to you, Sonika.
I suddenly just now is it fine, sir? Is it visible?
Yes.
Okay, so shall I start, sir?
Sure, please.
Okay, so good afternoon to all. So first of all, thank you for giving me this opportunity to speak here. So today in this talk, I'll be talking about linear independence of numbers. So more precisely, I'll be talking about linear independence of some special values of digamma function, logarithm of gamma function. But before that, we'll discuss why we are interested in the linear independence of these numbers and what do we actually mean by the linear independence of numbers. Like suppose if we take two numbers, like 1 comma root 2, we know that root 2 is not a rational multiple of 1. So 1 comma root 2, these are linearly independent over the field of rationals. And in this case, we can see that out of these two numbers, one number, that is the number 1, belongs to the field Q, that is the field of rational. But suppose if I take two numbers, say root 2 and root 3, these are linearly independent over the field of rational. But in this case, both the numbers are irrational, like none of them belongs to the field of rational numbers. So likewise, similarly, suppose we have the notion of linear independence of vectors, we have linear independence of number also. Like here, if you consider a set of say n elements, say alpha 1 to alpha n, and when we say that these numbers are linearly independent over the field K, that means they do not satisfy any non-trivial relation of this particular form where this Ci belongs to the field K. Now that is the definition of linear independence of numbers. But what do we actually mean by that here? Since we are interested in something called algebraic or the transcendental nature of numbers. So before going to the linear independence definition, I'll discuss what do we mean by algebraic numbers. So suppose if we have any number alpha and we can find a polynomial with rational coefficients such that it is a root of that polynomial, then those numbers are called as algebraic numbers and they form a field that is called as the field of algebraic numbers, and rest of the numbers are called as transcendental numbers. And in this talk, we are basically interested in finding the arithmetic nature, that is the that is the algebraic or the transcendental nature of numbers. So if you have a collection of say n elements, alpha 1 to alpha n, and that are linearly independent, say over the field of rationals. So this means that out of those collection, at most one element can belongs to the field Q, and hence rest of the numbers are linear, are irrational number. Now, if I replace that field, say with rational to field of algebraic numbers, that means in that case we are saying that in that collection at most one number can be algebraic, and hence at least n minus 1 many elements are transcendental in nature. So that is the meaning of linear independence numbers over some specific field K. Now, if in that collection, if I add say any rational number, say 1 or say 2, if I add 2 comma alpha 1 to alpha n, and if I prove that these numbers are linearly independent over the field of say algebraic numbers, then all the alphas are transcendental in nature, because we already found one element and we can have at most one element that can be algebraic. Now, why we are interested in studying the linear independence, that comes from here. Like suppose if you consider the series, the harmonic series, we know that this harmonic series diverges. But if you replace that coefficient 1 with plus minus 1 in the sense, which is a period 2 here, if you see, because minus 1 to the power n minus 1 by n, then this series converges and its value is log 2. And we know that log 2 is transcendental. So not only this series converges, but the sum is equals to a transcendental number. Now, the obvious question is, instead of plus minus 1, like here we have a period 2, suppose we have any finite period, say q, then in that case, what happens? So in that case, in 1964, Erdos, he made a conjecture that if f is any periodic function with period say q, and if it takes plus minus 1 values and 0 when q divides n, then in that case, this series sum will not be 0. And in fact, here he took the function which takes plus minus 1 value. And in 1969, Chawla proposed another question, that what happens if instead of plus minus 1, it takes some rational values. So he proposed the question that does there exist any rational valued function for which this series, if it converges and it converges to 0. In this talk, we are not basically interested in the L function. We are more precisely focusing on the linear independence. Like here, suppose if you consider summation, like previously we have summation 1 by n. Now if we have instead of 1, n square is there, n cube is there, then in that case what happens? Like summation 1 by n square. Here also we know that summation 1 by n square converges, and this value is pi square by 6. So now instead of 2, suppose if we have any k, so in that case it is defined like Lk of f, and if we are taking any periodic function, then in that case what can we say about the arithmetic nature or the vanishing or non-vanishing of these particular series if it converges? Then in fact these type of series are extended for the complex plane also. The Dirichlet series associated to any function f with period q is defined as L of s comma f is summation fn by n to the power s, where this real part of s is greater than 1. And in fact, by using the Hurwitz-Zeta theory, one can extend it to the whole complex plane except for the when s is equals to 1, real part of s is equal to 1. In that case, we have when s is equal to 1, we have pole is there with residue that we will see later. And in that case, if the residue is 0, then one can study the arithmetic of those series. Since it is extended to the complex plane, one can talk about the derivative also. So basically, we are interested in the arithmetic nature of these series as well as their derivative. So in this talk, I'll be focusing more on the case when k is equal to 1. So when the case when k is equal to 1 was thoroughly studied by Murthy and Sada in 2007. And he proved that if you take f to be any periodic function with period say q, then this series summation n by n, this series will converge if and only if this is the residue part. That means the residue part is equals to 0, because that is s is equal to 1, we have a pole is there. So if the residue is equal to 0, then in that case the series will converge, and the value of the series is equals to summation a is equals to 1 to the power q f of a psi of a by q, where this psi is basically the di-gamma values, which are defined as the logarithmic derivative of the gamma values. So far we know there is something called linear independence of numbers. Now we have got some numbers which are psi of a by q. If we know the linear independence of psi of a by q over some specific field, then we can talk about the vanishing or the non-vanishing of L1f. So basically we can see that there is a one-one kind of relation about the non-vanishing of this L function and the linear independence of these di-gamma values over some specific number fields. These FA belongs to those number fields that we'll see later. Now, so far we have considered the case when k is equal to 1. So now the case is like instead of L1f, what happens if the derivative also comes into the picture? Like here, if f is any periodic function, and this f hat is the Fourier transform of that function. Then in 2009, Murthy and Ruff, they proved that the derivative of L functions at s is equal to 0 can be written in terms of L1 of f hat, and which can be done in terms of the logarithm of gamma values, where f is any rational valued function. Now note that L1f, we already have something called in terms of di-gamma values. Why we require now L1f in terms of logarithm of gamma values? That we'll see later, because we are basically studying some Dirichlet type of functions. So if f is Dirichlet type, f hat may not be Dirichlet type. So in that case, whatever the results are known for the Dirichlet type are no longer can be used for the Fourier transform of function like L dash of 0, f. So that is the reason now we have to study it in terms of something called logarithm of gamma values. So far we have got type of numbers. We have gamma values, we have logarithm of gamma values. So if we can study the linear independence of these logarithm of gamma values and these gamma values, digamma values, sorry, then we can talk about the vanishing and non-vanishing of these derivative L function in L1F. Another important case is for the case when S is equal to 1, then any higher derivative was studied by Hofmacher in 1978, and he proved that likewise for the case when k is equal to 0, L1F by Murthy and Sada, they proved that that can be written in terms of digamma function. Here, L dash n to the power k, where k is the kth derivative, and in that case, it can be written in terms of the generalized till j is constant with this psi k of a comma a by q. These are the generalized till j is constant. And till now, I don't think even the irrationality question of these type of these constant is known. Now, another important thing is that we have come across gamma function, digamma function. We have come across logarithm of gamma function. Why this logarithm of gamma function is important? For the case k is equal to 1, even the derivative of L functions like L dash of 1 comma f can be represented in terms of log linear combination of gamma function for the case when f is an odd function. And this was done by Murthy and Pathak in 2018. Now, if you see in this one, if you consider the first term, for any fixed q, this is basically a constant. And for this constant, there is an algebraic term is attached. And then we have log linear combination of gamma values. So one can get rid of this term, that a constant term attached with the algebraic term. If we take two functions, say f1 and f2, and then multiply by the suitable constant, we can get rid of these numbers. But the main thing is that how can we solve these kind of equation? Like, what can we say something about the logarithm of gamma values? So if you see so far, we have come across two type of functions, gamma function, digamma function, sorry, and logarithm of gamma function. So one can talk about the non-vanishing of gamma of L1F by using the digamma function, because L1F can be written as a log linear as a combination of digamma function. Another thing is that when f is an even function, then L dash of 0 comma f can be written in terms of linear combination of logarithm of gamma function. Similarly, for odd function, we have seen and for odd function, we have seen that by using the result of Hofmacher, that can be written in terms of the this something called generalized till j is constant. So likewise, we have something called digamma function. We have for the derivatives, we have generalized till j is constant. So we are also interested in knowing the arithmetic nature of these generalized till j is constant. And there are some known results in the direction of like when f is an odd function and the linear independence of L dash of 1 comma f. But that whatever the results are known, that are known under the assumption that this logarithm of gamma values are linearly independent over the field of rationals as well as even for the field of algebraic numbers. So under the assumption of these conjectures, they have proved the transience of the generalized till j is constant and the linear independence of L dash of 1 comma f. Now, we have seen the conjecture of Erdos and even the question proposed by Chawla. Now, to answer those like partially, in 1973, Baker, Birch, and Bursting theorem, which is a famous theorem in number theory, that says that if you take f to be any periodic function with period say q, and that supports only at the co-prime values, that means at the known co-prime values, it is taking value 0. And another condition that they have assumed is that the field generated by the coefficients Fi over the field of rationals has a trivial intersection with the cyclotomic field, then in that case, the series sum will not be equal to 0. Now, if you take say Q is equal to P, then in that case, the Chawla's condition that the function should belongs to the function taking rational values, then in that case, the intersection with the cyclotomic field will anyway be trivial, that rational only and the GCD of n comma q, that is because p is prime, that is also satisfied, and hence this answers Chawla problem that there does not exist any rational valued function such that this series is equals to 0. And it also answers Erdős question for the case when q is equal to prime. But note here that in this theorem, they have assumed at the co-prime conditions, it has to be like at the known co-prime condition, the function has to be 0. Another thing is that they have taken the intercept trivial. So the question is why these two conditions are important. So can we find some other sufficient conditions, like instead of this one, like suppose their intersection is some bigger field instead of the field of rational numbers, then what happens? Now, before going to these results, we'll start with the digamma function because we are interested in finding the non-vanishing of L functions. So we'll be starting about the digamma function. So the digamma function is defined as the logarithmic derivative of the gamma function. And this digamma function, and we'll see later that whatever the results are known for this digamma function is always digamma plus the Euler constant. Note these two functions, not these two constants separately, because this Euler constant, we don't know even the irrational equation, like whether it is rational or irrational. So instead of studying them separately, we'll see that most of the people have studied them together, like psi of x plus gamma. And in that case, these are termed as harmonic numbers. So in our later section, we'll study them in terms of harmonic numbers instead of the digamma function. Now, one important result that is not in the direction of this digamma function is the Gauss identity. And he proved that for the case when a by q is a rational number and with GCD of a comma q is equal to 1, then this digamma function at these rational arguments satisfy this particular identity. Now, if you see in this particular identity, we have a Euler constant is there. We have a log linear combination of algebraic number. We have a pi term attached to some algebraic number, plus we have a log combination of again some algebraic number with algebraic coefficients are there. Now, since we don't know about the nature of this constant Euler constant gamma, so what we'll do is we'll take this Euler constant gamma onto the left hand side. Then we are left with a log linear combination of algebraic number plus pi term is there. And one can study the transcendental nature of these type of numbers by using Baker theory, because Baker theorem says that if we have a log linear combination of algebraic numbers, then this sum can either be 0 or a transcendental number. And if we can show that this constant is non-zero, then in that case it has to be a transcendental number. So that is one way of proving that psi of a by q plus this Euler constant gamma is transcendental in nature. In 2007, Ramurthy and Sada, they proved that this psi of a by q plus gamma, these are transcendental in nature. In fact, there is one beautiful application of Baker's theory by Ramurthy and Sada in 2009 that was after this result of this psi of a by q plus gamma. And by using that application, one can directly say that these numbers are transcendental. And that application of Baker's theorem, that proposition says that if you take any log linear combination of algebraic numbers, like log linear combination, then by Baker theorem, this sum is either 0 or transcendental. But if you take log linear combination of some alpha i's, where these alpha i's are positives, and we have a pi term is also there in the picture, then this sum will always be non-zero. And by using Baker theorem, then it has to be transcendental. So one can use that application of Baker theorem to directly say that these numbers are transcendental in nature. But here he has given a different proof to prove that these numbers are transcendental in nature. Another thing that he proved that now here they have proved that transcendental. Now the next step is what can we say about the linear independence of these numbers? So in that case, they proved that if you take K to be any algebraic number field and its intersection with the cyclotomic field is Q only, that means trivial, then in that case, these numbers are linearly independent over the field K. That one can see directly by using Baker-Birch and Worsing theorem. Because if suppose these numbers are linearly dependent, then that means there exists some CAs such that if you take the combination of those numbers with psi of A by Q plus this Euler constant gamma, then you get a non-trivial relation. That means CAs are not all zeros. Then you can define a function which will be a Dirichlet type function that will satisfy the condition which are there in the Baker-Birch-Worsing theorem and define that function f such that f of a is equal to CA. Then in that case, Baker-Birch-Worsing theorem says that this series sum can never be zero. And hence, since the series sum can be written in terms of the digamma values by using the theorem of Murthy and Sarda, so that means this sum can never be zero, and hence these are linearly independent over the field K. So that follows from the Baker-Birch and Worsing theorem. But note here that one important thing is there. They have talked about psi of A by Q plus this Euler constant gamma. Because we don't know about this Euler constant gamma, so that is why they have taken Euler constant gamma together, and then we are left with log linear combination where we can use Baker theory. Now the question is that when this Euler constant gamma is not a part of the family, that means now we are studying only psi of A by Q instead of psi of A by Q plus gamma. Then in that case, they made a conjecture in 2007, which we call as Murthy-Sarda conjecture, and they conjectured that if you take psi of A by Q, all the co-prime values, and take K to be any algebraic number field, again which has a trivial intersection with the cyclotomic field. Another thing is that why they are taking this trivial intersection with the cyclotomic field, that one can see by using this identity, Gauss identity. Because if you see in this Gauss identity, what are the coefficients of logarithm of sign values? These are cos of 2 pi Na by Q, which are basically the elements from the maximal real cyclotomic field. So to avoid that, they have taken the coefficients in such a way that from a field which has a trivial intersection with the cyclotomic field. So that is one of the reasons that K intersection Q zeta Q has to be Q only. Yeah. So in that case, when we are talking about only psi of A by Q, they conjecture that these numbers are linearly independent over the field K. And one beautiful observation of this conjecture is that if this conjecture is false, then gamma will be a Baker period. And Baker period means gamma can be written as a log linear combination of algebraic numbers. And since gamma is non-zero, that means by Baker theorem, it has to be transcendental in nature. But this doesn't seem possible because we already have a conjecture by Don Jaeger where he conjectured that gamma is not a period. So it can't be a Baker period. So in that sense, one can take that either this gamma cannot be a Baker period because otherwise the conjecture by Don Jaeger will be false. So, but that is an observation from Murthy and Sarda conjecture that either this conjecture is true or we have gamma is a Baker period. Now, in this direction, this Murthy-Sarda conjecture, there have been some improvements by Gunmurthy and Ruck in 2009, and they proved that if you take two numbers, say Q and R, which are co-prime to each other, and K to be any algebraic number field, again with the same conditions that are there, like the intersection with the cyclotomic field has to be trivial only, then corresponding to each set, to each number, we have a set like psi of A by Q, and for corresponding to R, we have psi of BR by Q. Then out of these two sets, at least one of the set will be linearly independent over the field K. So since Q and R are co-prime, they have used the norm idea to prove that out of these two sets, at least one set will be linearly independent over the field K. But now what happens if Q and R are not co-prime and there exists infinite family of integers which satisfy those conditions for which this theorem doesn't tell anything. Now, here like in the starting, we have mentioned like till now we are assuming the fact that we are taking psi of A by Q, like here also psi of A by Q, where GCD of A comma Q is equal to 1. So one thing is that why we require this co-primality condition. What happens if we remove this condition? So if we remove this condition, then in that case, we can find example like here, if we take q is equal to 6, then we have found a non-trivial example for such that the psi of a by q satisfy a non-trivial relation over the field of rational. Another addition that we have assumed in this particular setup is that the k intersection with the cyclotomic field has to be q only. Now what happens if it is not q? Then in that case also, we have found examples like if you consider k is equal to q root 2, then in that case, its intersection with the q zeta 8 will be non-trivial, that is q root 2, and over that field, we have found a non-trivial relation between the digamma values. So that is the reason that both these conditions are required, both these assumptions are required. But here one question arises that k intersection with the cyclotomic field is q. So what happens if it is not q, but some field, say k1, which properly contains the field of rational numbers and sitting inside q zeta 8, then like how much we can extend? In the sense, that is one question arises, because I have considered the cases for the 2 to the power n, and for some cases I tried to solve this one, and what I have realized is that here also, if you see that their intersection cyclotomic field is basically the maximal real cyclotomic field. So if the intersection is not maximal real cyclotomic field, some field smaller than the maximal cyclotomic field, then what happens? Because whatever examples like till now I have seen, most of them are like their intersection is coming out to be a maximal real cyclotomic field. If it is not maximal real cyclotomic fields, will that conjecture still be true or not? So that is one question that arises from here. Okay, so since we are studying these numbers over the field K, which satisfies some conditions. So since we are interested in the transcendental nature, so the obvious question is, what happens if we study their linear independence instead of over the field K, but over a bigger field, say a field of algebraic numbers, because we are interested in the transcendental nature. So instead of studying over the field K, here I have considered the field to be the field of algebraic numbers. And in that case, we have proved that suppose if you take J to be any finite set of 4 primes, and now take H1 and Haji by Qi. Basically, we are taking all the digamma values, because now we are studying those digamma values in terms of the harmonic numbers. And now here we are not putting any condition on GCD of A, Q is equal to 1. We are taking the whole set of numbers, and then we are studying that take the vector space spanned by these numbers for any finite set of primes. Then in that case, define this Wj to be the q-bar span of these numbers. Then the dimension of this vector space in this case turns out to be exactly phi qi by 2 plus 2, where this summation is from 1 to n. Basically, if you consider n is equal to 1, that means the dimension is phi q by 2 plus 2. So initially, we have psi of a by q and GCD of a, q is equal to 1. So we have exactly phi q many elements are there. Now, as soon as you go to a bigger field, the field of here algebraic numbers, the number reduces to half. Plus 2, why this plus 2 comes into the picture? That is because of the fact, like if you see in this identity, Gauss identity, we have this n is equal to 1 to q minus 1 by 2. This is exactly phi q by 2 when q is a prime number. And these are logarithm of sine pi by q. These values are basically some cyclotomic units. Like we can modulo by the sine pi by q, we can make them as cyclotomic units. So basically we are studying the linear independence of the multiplicative independence of cyclotomic units. And if we add log, that means we are studying the linear independence of cyclotomic units. So we have phi q by 2 comes from this particular part. Now we have extra 2 terms are there. Psi of a by q, this Euler constant is already on the left hand side. Now we are left with 2 terms, log 2q and pi by 2 quote pi a by q. Now we have shown that this log 2q and this pi term, these are also linearly independent with this logarithm of cyclotomic units. So in total, we have phi q by 2 plus 2 elements are also there. These are all of them are giving some linear independence relation, and from there the dimension comes out to be phi q by 2 plus 2. And here we have generalized it to any finite set of primes. Now, the previous one was for the case of any finite set of primes. Now the case is when if instead of primes, what happens? We have prime powers. So for the case of prime power, that idea, like logarithm those numbers turns out to be linearly independent is not going to work because if you see in this one, for the case of prime power, say q is equal to p square minus 1 by 2. So we have these many elements are there, and the logarithm of sine pi n by q, these are no longer linearly independent. So that means we have to find a maximal linearly independent set here. And the co-prime elements are going to give us the maximal linearly independent set. That means we have to remove the known co-prime values. So to remove the known co-prime values, we have made something called as variant of Gauss identity. Like here, if you see, if you take p to be any odd prime and n any natural number, and now we are studying the case p to the power n. So here I am considering s to be all those numbers which are co-prime to p to the power n by 2, like which are less than p to the power n by 2, the first half many, and co-prime to p, and we call them as BIs. So then we get an like instead of Gauss identity, we call it as a variant of Gauss identity. Here h of a by p to the power n. If you see, we have a log term is there, we have a pi term is also there. Plus, if you see here, we have logarithm of sine pi bk by p to the power n. So bk now are relatively prime to p. So now we have exactly 5p to the power n by too many elements are there, and we can show that these are linearly independent over the field of rationals, and then by using Baker theorem over the field of algebraic number also. Another thing is that previously we have attached to these numbers, we have something called cos value. One cos value was there. Now we have a combination of cos values, and cos values were coming from the maximal real cyclotomic field, and that were forming a basis for the maximal real cyclotomic field. Here also we have proved that these numbers are forming a basis for the maximal real cyclotomic field. And why this property is important, that these numbers should be a basis, that we'll see later. Now for the case of prime power, we have the following result. Like if you take J to be set of any odd primes and their power also, and you define again like a vector space like we have defined earlier to be the Q bar span of all those numbers, and phi j here I have defined to be phi of pi by mi by 2, then the dimension of this vector space wj minus phi j is either 2 or 3. So previously the dimension comes out to be phi p by 2 plus 2, but here the dimension can be phi p by 2 plus 2, or it can be plus 3 also. And in fact, these both values are attainable. Like if you consider j is equal to 3 square, then in that case, the dimension of this vector space wj is exactly phi p by 2 plus 2. And when you consider 5 square, then this value is 3. That means their difference is equal to 3. That means both the values are why the previously I said like these are forming a basis for the maximal real cyclotomic field. So why these are important? In order to solve these, like here I have proved that these numbers are linearly, like this is the dimension of this particular vector space. So we have found a basis. We have found first a set which is forming a basis. So first we have to show that that set is linearly independent. Likewise, we prove linear independence of vector. Here also we'll consider that their linear combination is equal to 0 with some constant attached, say Ci's. And if their combination is equals to 0, like in vector space, we get a metric equation. Here also we'll get a metric equation. And to show that these are linearly independent, we need to show the determinant of that matrix has to be non-zero. Here also we'll get a matrix of this particular form, and we have to show that this matrix is determinant of this matrix has to be non-zero. And since we have known that these elements are forming a basis for the maximal real cyclotomic field. So the determinant of this matrix has to be non-zero, and hence the numbers that we have found turns out to be linearly independent. And then we have shown that these are forming a basis. Another thing is that, like for the digamma function, we have shown that psi of a by q, where GCD of a comma q is equal to 1. Those numbers are linearly independent, like only when GCD of a comma q is equal to 1. Now here we have proved that if you take first Pp by 2 plus too many elements, like harmonic numbers, here we are not putting any condition on a and p. So suppose if we have any prime, say p, and h of a by p to the power n we are studying, where a is running from say 1 to p to the power n. So if you take first phi of p to the power n by 2 plus too many values, that turns out to be a basis for this vector space. So till now, like even for the non-vanishing of L function, whatever function we were studying were mostly like Dirichlet type function. The obvious question is, if the function is not Dirichlet type, then what happens? Like, can we talk about some function which are supported only at say phi of p to the power n by too many values? Then can we talk about the linear independence? The non-vanishing of those L functions. So in general, like we don't know, but at least for this particular case, if you take the function f such a way that it is supported only at the first p of p to the power n by too many values, then it will be L dash of 1 comma f will be non-zero. So instead of studying Dirichlet type, one can study a different type of function also. So that is one application of the basis that we have found for these particular vector spaces. Now for the case of product of primes. So as soon as we go for the product of primes, say product of 3 primes or 4 primes, then the cyclotomic units are no longer multiplicative independent. And that is one of Ramachandra units comes into picture, because these cyclotomic units are not multiplicative independent. And it was Pei and Feng who characterized the set of integers for which these cyclotomic units are multiplicative independent. And they proved that as soon as you go to any integer which has more than 4 prime factors, then the cyclotomic units are no longer multiplicative independent, and hence this idea is not going to work there. Now for the case of product of primes, like when we have 2 primes, then in that case also they have given some necessary condition that if the primes are satisfying, the factors basically are satisfying those conditions, then only the cyclotomic units are multiplicative independent, and hence we can talk about the linear independence of these harmonic numbers. So for the case like when m is a product of 2 primes, p1 to the power alpha 1 and p2 to the power alpha 2, and we satisfy these conditions, and this p1 and p2 are congruent to 3 modulo 4, and these are semi-primitive. Like primitive root means its order is phi of p to the power alpha 2. Semi-primitive is order of p2 to the power alpha 2 by 2. And in that case only, the cyclotomic units are multiplicative independent. And hence we can use these conditions to prove the dimension. So for the case when it is product of 2 primes, instead of finding the exact dimension, we have found an upper bound for the dimension of the vector space spanned by the product of 2 primes. Like here, if you have J to be the set of any natural numbers, like the natural numbers which satisfy property 2, basically we are considering all those numbers which have exactly 2 prime factors and which satisfy some condition. And if you take Wj to be the Q bar span of these numbers, then here the dimension of this vector space will be bounded by phi of mi by 2 plus n plus 3 here. So that is like here we have found an upper bound. One can found a lower bound also here. Like previously we have 2 cases. We have the difference between the dimension of this vector space Wj and that quantity phi j, either 2 and 3. Here also the difference, in that case we have 3 possibilities. It can be 2, 3 and 4 like that. So but one can found a lower bound also. Now so far we have considered the case when these the linear independence of these harmonic number, or basically the digamma function over the field of rationals, over the field of algebraic numbers. We have already seen that there is a conjecture by Murthy and Sarda in which they conjectured about the digamma values, not the Euler constant, that these numbers are linearly independent over the field K, and some improvements that we have already seen by Gunmurthy and Rath. Now, in this direction, we have proved that this conjecture will always be true, but with at most one exception. Previously, it was proved that when Q and R are co-prime, so still there are infinitely set of integers are left for which we can't say anything about the conjecture. Here we have proved that except with at most one exception, this conjecture will always be true. And in fact, not only this, the observation that I mentioned there, this either gamma is the Baker period or this this conjecture is true. So in that case, we have incorporated both the cases, whether gamma is the Baker period or not. In both the cases, we have found that the conjecture will be true with at most one exception. In fact, I think one can remove this exception also, and it will turn out that doesn't matter whether your gamma is a Baker period or not. This conjecture will always be true. So one of the way to check or to solve the rational or the irrationality problem about this Euler constant gamma is not going to work here, because this conjecture anyway will be true. So initially we started with two type of values, constants, the digamma and the logarithm of gamma values. The digamma comes as a combination for L1f and the digamma for the derivative part. Logarithm of gamma values as the derivative part. So why this logarithm of gamma values are important? And there are some conjecture, in fact, non-result in this direction also. Like Rohlich, he made a conjecture that any algebraic relation, any multiplicative dependence relation between the gamma values will be consequences of these three relations, like either the translation property or the reflection property or the multiplication property. So any relation, dependence relation satisfied by the gamma values will be a consequences of these three relations. Now, this only talks about if there is any relation, then if there is any dependence relation, it will be consequence of these three relations. Now, Rohlich and Lang together, they made a conjecture about this gamma values, that if you take the field generated by these gamma values and if you join pi also, then the field generated by then the extension of q bar generated by these gamma values has transcendence degree phi q by 2 plus 1. That plus 1 is coming from the pi, and these are the psi of a by q. So that is the transcendence degree. Now, in order to solve these problems, and plus this logarithm of gamma values already coming as a part of the derivative of L function, in 2009 and 2011 also, in 2009, Gunmurthy and Rath, they made a conjecture, which they call it as variant of Rohlich conjecture. And they conjecture that instead of studying gamma values, they studied the logarithm of gamma values, because they have a logarithm of gamma values have a beautiful application for the derivative of L function. And they conjecture that that if you take logarithm of gamma values and take the vector space spanned by those logarithm of gamma values, here GCD of a comma q is equal to 1, then the dimension of this vector space is phi q. Basically, they are saying that logarithm of gamma values a by q, where GCD of a comma q is equal to 1, are linearly independent over the field of rationals. Later, they extended this conjecture to the field of algebraic number also. And over the field of algebraic number also, they conjecture that these numbers will be linearly independent even for the field of algebraic number also. Now, under the assumption, why these conjectures, these variant of Rohlich conjectures are important, because under the assumption of these two conjectures, Siddhi and Ramurthy in 2018, they proved the linear independence of the derivative of L function. As we have seen earlier, that linear independence of the derivative of L function for the case when k is equal to 1 is related to the logarithm of gamma values. And they assume that if the conjecture is true, and if you take F1, Fr to be Q linearly independent, which satisfy these conditions, and for F is an odd function, in fact, they have proved result when L of 1 comma F is equal to 0 also, then in that case, if you consider this particular set, then out of this set, at most 3 many elements can be algebraic, and hence the rest of them has to be transcendental. But this is under the assumption of the conjecture 2, that means logarithm of gamma values are linearly independent over the field of algebraic numbers. Even they talk about the transcendence of this generalized Still constant for the case when k is equal to 1. In here, they assume that this conjecture is true, and in that case, if you take 1 of a comma p, then at least p minus 7 by 2 many elements are transcendental in nature. Now, in the direction of these variants of Rowley conjecture, there have been some improvements made by Gunmurthy and Rath in 2011, and they proved that if you take Q to be any prime power, then the conjecture says that the dimension of the vector space has to be exactly phi q. They have proved that the dimension of this vector space spanned by these logarithm of gamma values over the field of rational is at least phi q by 2. And since they have extended that conjecture to the field of algebraic number also, now over the field of algebraic numbers, they have proved that if you take Q and R to be two distinct primes, then the dimension of at least one of the subspace is at least phi q by 2. Again, here they have taken Q and R to be distinct primes, and they have used norm idea to prove that dimension of at least one of the subspace has to be at least phi q by 2 or phi r by 2. Now, what happens if Q and R are not like distinct prime powers, like maybe same prime with distinct power? Then in that case, they have assumed Shanwell conjecture, and they proved that under the assumption of Shanwell conjecture, the dimension of this vector space over the field of algebraic numbers is at least phi q by 2. Note that here, even after the assumption of Shanwell conjecture, we have come to phi q by 2, not the whole dimension, in the sense like we have proved that the conjecture will be true. Another thing is that they have used Shanwell conjecture, which we know that it is a very far-reaching problem. So now, to prove this thing, what they have done is that they have divided the whole vector space into two subspaces, V gamma of Q plus and V gamma of Q minus. And they proved that if the conjecture is true, then dimension of both the subspaces has to be exactly phi q by 2, and as a whole, the dimension of the whole vector space will be phi q. Now, they proved that for the positive subspace, the dimension of this vector space is exactly phi q by 2, and hence the dimension of the whole subspace is at least phi q by 2. That is the idea they have used to prove that the dimension is at least phi q by 2. Now, in this case, we have also made some improvement, like for the case of this, when Q is a prime power, then they have used Shanwell conjecture to prove this one, or when Q and R are distinct prime powers. Now, the obvious question is when Q and R are same prime powers, then in that case, we have proved that the dimension of the positive subspace is phi q by 2, and hence, as a whole, the dimension of this vector space is phi q by 2 here, but we have taken with like one exceptional Q. Like here, we have taken all the prime powers with at most one exception, and then without using Shanwell conjecture, we have proved that the dimension of this vector space is at least phi q by 2. But more important than that, we have proved that this conjecture is not true in general. We can find counterexamples, like here, if you consider Q is equal to 55, and I have divided the set of like all the numbers which are co-prime into two sets, like S1 and S2. Basically, we have defined a function which is an odd function, and which takes plus minus 1 values, and at these points when a belongs to S1 and when a belongs to S2, it is 1. Then if you take the log linear combination of these numbers with fa satisfying these conditions, then we see that this satisfy a non-trivial relation over the field of rational, and hence this conjecture is not true for the case of rationals, because our FIs are coming from rational numbers. And since it is not true over the field of rationals, so that means it won't be true even for the case of algebraic number also. In fact, we have found a infinite set of example for which this conjecture is not true. Basically, we have proved that if q is any positive integer with at least 4 prime factors or more than with at least 4 prime factors, then this conjecture will not be true, because in that case the same idea we can use, that the cyclotomic units are no longer multiplicative independent, because here we are studying logarithm of gamma values. When f is an even function, logarithm of gamma values. So we have logarithm of, like here, logarithm of a by q plus logarithm of this one. So we can use the property of the gamma values and we can write it in terms of the sign values. Now, instead of studying in terms of the logarithm of gamma values, one can study in terms of logarithm of sign values. And one can study in terms of logarithm cyclotomic units. And since those units are not multiplicative independent, so we can find counter examples. So the case when it is at least 4 prime factors, then this conjecture is not true. But we don't know when q has say 3 prime factors, or like q is a prime power or prime number like less than 3 or less than or equals to 3. So in that case, we don't know whether the conjecture is true or not. And similarly, since the conjecture 1 is false, the conjecture 2 will also be false, because conjecture 2 implies conjecture 1. So in that case also, and to prove that these conjectures are not true, what we have done is that we have shown that the dimension of the positive subspace is strictly less than 3q by 2, and as a whole, the dimension of the whole subspace will be strictly less than 3q, and hence this conjecture is not true. But note that for the case when q is a prime, in that case, nothing is known. In fact, the results that were proved by Siddhi to prove the is constant, she proved it only for the case when q is a prime number. So for that case, she proved that the dimension of that vector space, am I audible, sir?
Yes, you are.
Okay. So she proved that the dimension of that vector space, only for the case of primes. But for the case of primes, we don't know whether this conjecture is true or not. Another thing is that she proved that only for the case of primes. But for the case of primes, it is coming in terms of Fourier transform function. Even if f is a Dirichlet type function, we don't know f hat is a Dirichlet type function or not. So even if this conjecture is true for the case of, say, prime powers, we can't use that conjecture to talk about the transcendence or the non-vanishing of L function, because as soon as you go to prime power, f hat is no longer a Dirichlet type function. So we can't use this conjecture, because this conjecture deals only with when GCD of a comma q is equals to 1. So that is one disadvantage, we can say, that in the sense we can't talk about the transcendence of these functions. And application of this is that since we have already seen that if f is an even function Dirichlet, then L dash of 0 comma f can be written as a log linear combination of gamma values, and that can be written in terms of logarithm of sign values. By using Baker theorem, one can say that this number can be either 0 or transcendental nature. That was proved by Gunmurthy and Rath. Now the question is, what happens, in which cases this L dash of 0 comma f will be 0 or transcendental. So when q is prime power, if f is not identically 0, then in that case, L dash of 0 comma f will be a transcendental number. But as soon as we go to product of 2 primes, we can always find some non-trivial example for which L dash of 0 comma f will be equals to 0. So here, these are some of the open problems, like that I already discussed also some of them. Like for the digamma values, firstly, for the digamma values, we have seen that intersection with the cyclotomic field is trivial. Then the Baker-Birch-Wassing theorem says that this series will not be zero. Now, if the intersection is non-trivial, like I said, like for the case of say 2 to the power n, it turns out that the coefficients are coming from the maximal real cyclotomic field. So suppose if I take K1, which is sitting inside maximal real cyclotomic field, then in that case, can we say something, or still the theorem will be true or not? That is not, I think it is not known about this thing. Second thing is that we have studied the harmonic numbers, and this digamma function. So digamma function, most of the results are known when this GCD of a comma q is equal to 1, and then one talks about the non-vanishing of L function, where f is a Dirichlet type. So what happens, like here for the harmonic number, we have found a basis which are not co-prime numbers. Like we have first phi q by too many values are linearly independent. So how one can relate it to the some L function? That means can we relate it to any L function where f is supported only at phi q by too many values? So, and can we talk about the non-vanishing of those functions? Another one is that to prove this Rayleigh conjecture, we have studied only the positive subspace. Nothing is known about the negative subspace, and in fact, the negative subspace is of much more importance, because even in the these result and some other results that are known under the assumption of this conjecture, they have assumed basically that this negative subspace has dimension exactly phi q by 2. Although in the statement says that they have assumed the variant of Rayleigh conjecture, but if you see in the proof, what they have assumed that even if this part is true, still we can talk about the non-vanishing of derivative of L function, but only for the case of primes. So these three are like open problem, and so this negative subspace is comparatively much more important in that sense. So thank you. Any questions, sir?
Okay. Thank you very much, Sonika. Are there any questions for her?
Hi, this is Vivekananda. Can you hear me?
Yes, sir.
Yeah. Hi, Sonika. This was a nice talk. So
Thank you,
I have you have studied like L at 1 or the derivative at 0.
Yes, sir.
Right. So I would like to know whether there are results in some other natural number. You talked about it at the beginning, like for example, summation 1 by n square is pi square by 6. Okay.
There are
So
some yes, sir.
yeah, so I wanted to know that whether that kind of thing has been studied. Like if you are taking periodic function, now
Yes, sir.
you instead of 1, like you are interested to know other even values or odd values.
Yes, sir.
Yeah.
I think there are some results like for the case, because when k is not equals to 1, then we don't even have this problem also, like because at k is equal to 1, we have a pole also. So although we don't have that problem also, and I have seen some results, like right now I can't recall those.
Okay.
The thing is that, sir, whatever I have studied in terms of numbers.
Okay.
Now the application part is basically how to relate the linear independence with the L function, that I haven't done. Like I have studied in terms of the linear independence of numbers. So one can relate it to the L function also. And even for the higher, say k greater than 1. So in that direction, I don't know much about these.
Okay. Yeah, here one thing was like Murthy and Sarada, they proved that L1 comma F is in terms of the linear combination of digamma function. That was maybe one of the motivation to study special values of digamma function. And like you have mentioned one more, I think those are in terms of logarithmic of gamma function. So yeah, those kind of results, maybe generalization of those kind of results. This one. Yes.
There are generalizations, for the for higher. I think we have some higher derivatives of digamma function also. polygamma function are also there. So they have studied in terms of something called polygamma. So we need to study, like here we have identity for digamma function, but we don't have any identity for like polygamma function, because there we have log to the power log term comes into the picture. Like here we
Okay.
have used Baker's theory. So they
Okay.
are like, as soon as you go to like k greater than 1, you have something called polygamma, and those comes into the picture.
Okay.
And those numbers we have logarithm some higher power. So how
Okay.
to deal with this higher power, that is one thing. Another,
Okay.
for the derivative, like here, that are there in terms of the generalized stages constant.
Okay.
Here, even for the case like when s is equal to 1 and like k is equal to 1, for that case also we don't know, because whatever the results are known, that is under the assumption of these logarithm of gamma values are linearly independent, like under assumption of some conjecture.
Okay.
So like under the assumption of some conjecture, these things are not known, like for this case also.
I see. I see. Okay. Thank you. Thank you so much.
Thank you.
Professor Ajit Iqbal Singh had written some messages in the comments. Professor, are you there?
Yes, yes. Okay. Happy Fibonacci Day to all.
Yeah, thank you.
It is today. Okay. And now I have put in 3 kinds of remarks. First of all, thank you for the wonderful talk, Sonika. And you know, I'm reminded of Ramurthy visiting IMSC and other places and interacting with us. Now, one thing is there, in spectral synthesis, these linearly independent sets are used. And what is spectral synthesis? Translation invariant subspaces of L1T or L1Z or L1G for any locally compact group. And they are also closed ideals. So closed translation invariant subspaces are closed ideals. Then their zero sets are determined in terms of their zero sets of Fourier transforms. And the set is called a set of spectral synthesis if there is a unique closed ideal with that zero set. And such sets, linearly independent sets and other sets, are useful for studying spectral synthesis. And I have given 2 classical books in the chat. One is by Graham and McGee. Other one is by John Benedicto. The one by John Benedicto is called Spectral Synthesis, and one by Graham and McGee is called Commutative Harmonic Analysis. And there is a lot of development after that also. This is back in 70s what I gave. That is one thing. Second thing is that I gave is interval filling sequences. A sequence lambda n is called interval filling if the reciprocals 1 by lambda n, the sum with coefficient 0 and 1, they fill an interval. And this idea was given by Kakea. So that means all the numbers will occur as sums. And you are only using 0 or 1 as coefficients, but instead of 1 by 10 raised to n, you are using, you know, 1 by lambda n. And such sequences, 1 by 2 raised to n, it fills interval and essentially uniquely. Other powers, 1 by q raised to n, for 1 less than q less than 2, they also fill interval, but not uniquely for certain q's. And for q equal to 3, interval is not filled in because it is half of Cantor set. Twice of Cantor set if you go. Okay, so that doesn't fill a sequence. And that is what I am wondering, you are concentrating on sum being 0 or not, or sum being algebraic or not. And here are these interval filling sequences. So you have to either discard them or consider them. And since it is Fibonacci Day, I gave you reference of P. Rebenbaum's paper in Ensine Mathematics, which uses reciprocals of Fibonacci numbers for interval filling sequences. Thank you.
Okay, thank you.
Thank you. Thank you, Professor Iqbal Singh. Any further questions?
Hi, I wanted to ask a question. Can you hear me?
Sure.
Yes, sir.
So can you go to like around page 10? I am just curious about the result of Baker. Yeah, this one. 9, I guess. 9.
Nine.
Page 9. So yeah, in this case, I'm interested about if you take F2B Dirichlet character, let's say modulo Q. So in that case, I'm interested in the like non-vanishing of L1 chi. So if you take F2B at Dirichlet character modulo Q, then certainly this first condition is satisfied because the Dirichlet character will be vanishing only for non-co-prime values. And I don't know about the second result. So will that be satisfied? Because in this, why I'm curious about that is that will straight away give you this prime number theorem in arithmetic progression. So does that give you another proof of that? So I don't know. So how serious is the second condition? So here you are saying that Q of this is the root of unity, and you are taking intersection with Q of. So, like, do you know how serious is the second condition, or can you just straight away deduce the result?
I think here because the special values of like Dirichlet functions are basically nth roots of unity,
Right.
right? So yeah, in that case, like we have to see if it is periodic of period Q, then it's a yeah, Qth roots of unity. Actually, it takes.
Yes. Yes.
Yeah.
So it will
So
be
in that,
actually primitive pure root of unity.
yeah, in that case, I
Yeah.
don't think this will be true.
Oh, okay. So you are saying that you will have intersection apart from Q.
Yeah.
So you cannot straight away deduce
Yeah.
that L1 chi is not your
Yeah.
interest. Yeah. Because otherwise it would give another proof of prime
Yeah.
numbers in
Yeah.
arithmetic
Right.
progression. Sure.
Yeah.
Nice. Thank you.